Ladies and gents, let's go ahead and get into the notes. Now, this is going to be part two. So, we've had a chance to talk about some of the basics of translations, reflections, and rotations, some basic theory, and now you've also worked through those three investigations. So, please make sure you're not going through this part of the video or taking these notes unless you've done those three investigations separately, the yellow, pink, and green ones. Otherwise, you may not understand exactly what's going on. So, the goal and aim of this video is to get you some information, help you consolidate some of the stuff you were talking about. Notice a big question here, the guiding question. I've actually combined the ones I had before. And so we're going to talk about the coordinate rules, algebraic rules, and formal rules of translations, reflections, and rotations, and also talk a little bit about how they all relate to one another. Because in the end, the big question is, like, how do you know something has been translated, reflected, or rotated? And just like a previous unit with proof, it's not so much like what we think is happening or we can see kind of happening, it's what we can actually prove is happening. And it turns out these three things in combination and in concert with one another is actually how you can formally prove a translation has happened. So let's slide over here. Let's just get into translation first. So we should note that probably the best way to actually understand how these three things work together is by an example. And so I'm actually going to start with the structural rule. And so if we kind of acknowledge that a translation is nothing more than a slide. Okay, so I'm taking this shape, in this case, this triangle, and sliding it around the grid a little bit. We can track that multiple ways, and we're going to start with the structural rule. And so the question is, like, what has to happen? How does this have to move in order for a translation of slide to have taken place? So you did this work on the investigation, and you found out that when you're moving these things, what you're really looking for is a vector. Now, because this is just an example, it doesn't really matter where this vector ends up. And so I'm just going to kind of pick a place, let's say like maybe right here. And so a vector has distance and direction. This is how you mark a vector on the map, the single-headed arrow. But this is how B point is going to be translated, being slid kind of like along that line. Now, for this to be a true translation, this has to happen for every single point. So if the B point travels along this vector, so does the C point, and then so does the, let me get this pasted, there you go. There's the A point. Now this is actually true for all the points along A, B, and C, but if we just track the vertices, the corners, then we should be able to have enough information to draw on the shape. Now you saw me copy and paste these, so you know these are actually going to be the same vector, the same distance and direction. But there's a way we can actually prove that too, and I'll do it here in yellow. If you look at where the B point started, okay, and you drop it straight down, then you move it straight over, we can track how far that's gone. Same thing with the A point over and the C point over. Okay? Now all these should be the same amount on each one, and we can certainly count them. And so this seems to go down 1, 2, and then over, well, that's a half. So 1, 2, 3, 4, 5, and a half. And so it goes plus 5.5 in the x, minus 2 in the y. And actually, they're all going to do that. So we go down 2, and then we're going to go over 5.5. So minus 2 here, 5.5 there. And so this is actually, you could prove these vectors, these brown vectors, are all going to be the same distance and direction, because certainly we can calculate the slopes now down to over 5.5. But we can also feed these into the Pythagorean theorem and confirm that these brown vectors are all the same length. Now we don't have to do that right now, but I'm just saying we could. Now since we're all moving all the points the same way, the resulting triangle, if I were to connect now these new values connected by the vertices, and of course label these A prime, B prime, C prime, we're going to have our new triangle. And so structurally, the structural rule for translations are going to be these brown vectors. And so we can kind of slide over here, the structural rule that has to happen. We can make a little note here that we must have congruent parallel vectors that move the preimage to the image. Okay, and so those are the things that we have to draw in. And the vectors what I'm talking about are going to be these brown lines that actually show like the direct path from B to B prime, A to A prime, and C to C prime. And so like for this particular example, the vector we're looking at is minus 2 and then comma 5.5, because again, that's how that moves. So if you remember from the investigation, This just means, let me write it a little bit smaller. This just means down 2 and then over 5. Well, 5.5. Okay. So like this ties into the algebraic rule in the second and the formal rule as well, because if you recall about the algebraic rule, this just tracks points or tracks coordinates. And so for this particular case, we have xy, and it's going to go to this new xy, and the vector kind of reveals, and the graph kind of reveals, we're going to take our previous x, subtract 2, and we'll take our previous y and then add 5.5. Okay? So even though we saw that on the grid initially, those tied both into the structural rules and the algebraic rules for translations. Now, as far as the formal rule, like the algebraic rule is fine if you have a grid. The structural rule is fine if you're going to draw that in. But we can collect that into this formal rule. And here's what this looks like. I'm just going to write it out the first time, and I'll explain it. And so the translation we call t, that uses a vector of travel, -2. A little bigger. Okay, so the translation we call t that uses a vector -2, 5.5, takes a previous triangle, or the pre-image triangle, triangle ABC, to our new triangle, A prime, B prime, C prime. Okay, and so this formal rule, and this is something that unfortunately we just have to be able to do. The T stands for translation. This stands for the vector, which is the important information. You can't have a translation without a vector. And again, the vectors are those brown lines that show the direction of travel from B to B prime. This guy right here is your preimage. And this guy right here is your image. And so when you're looking at all this together, it should start to make a lot of sense. If we know that the coordinates are all changing by going down 2 and then over 5.5, like you see here in your algebraic rule, that means we are showing vectors, and that vector information is -2, 5.5, which is exactly like the algebraic rule. And we can collect that in a formal rule where that vector again shows up once more. And so for translations, the key phrase, the key idea is vector of travel. And so if you're going to have a translation, we're going to travel along vectors, and those vectors are going to be parallel. Are going to be parallel, and they're going to be congruent. And so they have to move it the same exact way and the same exact direction. And really that's all that we're seeing here with these rules, is that we're traveling the same exact direction and the same exact distance. Which is why we use a vector. Because vectors do those two things, all right? So that's translation. Let's talk about reflection. So again, I think where we're going to start is with an example, with a structure. And so to form a reflection, we're going to need a couple things. One, we're going to need a place to flip over, and that's going to be, it's called a couple different things. Sometimes we call this a line of reflection. Sometimes we call it a line of symmetry, but it all amounts to the same thing. Okay? We need somewhere up over which to travel, because remember, this is going to be a flip. So if you're thinking about like a reflection, excuse me, this is just like a flip. And so the first thing we need structurally is something to flip over, and so that's what I provided here. We can make a note this thing is called a couple different things: a line of symmetry, or a line of reflection. Okay? Either way, this does actually have an equation, and it's important to note that equation. This is going to be x equals 2. And so remember, x equals equations are vertical lines, and so that equation is x equals 2. So now if we're going to move our points, we have to move them over this line. Now another key feature of reflections is that the distances have to be the same, and here's what I mean. And so if you take point C and you travel it to the line of reflection, that's the distance of 2 boxes. And so if we want a new point C, we got to travel another 2 boxes, but on the other side to make this C prime. We can also note, as we zoom in here, that in addition to these being the same distance, they also have to interact with our line of symmetry in such a way that it's going to be a right angle. We can do that again with the line above. So if you take B, we're traveling a half, and then 1, 2, 3, 4. And so that's a distance of 4.5. So we have to travel 4.5 on the other side. So 1, 2, 3, 4, and then another half. And then we'll end up here at B prime. So you can already start getting a sense of what our shape is going to look like. Right? And so we know we just have to have another point somewhere out here. Right? Now to find that, we'll do the same thing we did with the previous 2 points. Now this one, fair warning, is going to overlap a little bit, but that's okay. If we go from A all the way to our line of symmetry, so it's 1, 2, 3, 4, 5, 6, 7. We have to travel 7 away from our line of symmetry. So 1, 2, 3, 4, 5, 6, 7. Okay? And that's where we'll put our C prime, or I'm sorry, A prime line point. And then we can connect it with the other 2 now. Okay? Just like the previous examples, these distances do have to be the same. They do have to be at a right angle with our line of symmetry. Same is true for the orange line, and so certainly this part of the orange, with a mark with 3 tick marks, is the same as this part of the orange. The orange kind of disappeared on us. Let me try that. Okay, so the same distance, and just like before, it's going to form a right angle. Now, as long as you see this happening, you have yourself a reflection. Um, and so we can consolidate that. So to be a reflection, you have to have a line of symmetry or line of reflection, okay? And that has to be a perpendicular bisector to the pre-image image line. Okay? In other words, the line that I draw from my pre-image to my image has to interact with the line of symmetry in such a way that it bisects and is perpendicular. And you'll notice it's true for all 3 of them. So it's certainly true for the BB prime line. It's certainly true for the CC prime line. The purple line of symmetry cuts that line in half. And then if I stretch this one all the way out from A to A prime, the purple line of symmetry again cuts that line in half and does so at a perpendicular angle. So that's what you're looking for in terms of your structure. And so as long as you can prove this has happened, then you can prove that you actually have a reflection. And so the structural rule here is 1, you have to have a line of symmetry. Okay? And that line of symmetry must be a perpendicular bisector. Perpendicular bisect. The pre-image image line. Okay? And again, this should make a lot of sense. The reason this should make sense is because if you're traveling a certain distance to your line of symmetry, you should be traveling the same distance directly away from it. And so the perpendicular part ensures directly away, and the bisecting part ensures the same distance. Now, as far as the algebraic rule, there are lots of algebraic rules for reflections. Like the one we have here in particular, x comma y, since we're just flipping over a line here, we're just going to be exchanging some points. And so the algebraic rule here, and they're going to be different every time. It's not like the translation rule where it's going to be the same every time. We're going to see some changing out of these points, of the x and y points. At least we're going to see some changing out for positive and negatives. Because if we're flipping over a line, what was positive may become negative and vice versa. And so I'm going to leave that open because it's just going to be different every time, but we're going to look for sign switches. Okay, and that's a good general way to tell if something's been flipped. If you're keeping the same numbers, but you're changing out the actual signs. Now, for a formal rule, for reflections, we're going to use a little r. So R stands for reflections. Just below it, just like with translations, we have to list the important information. And in this particular case, the important information is going to be our line of symmetry, which is going to be x equals 2. Okay, we have to identify a pre-image, which was triangle ABC. And we have to identify our image, which is going to be triangle A prime, B prime, C prime. And so again, that R stands for reflection. This is going to be important information. The one that basically identifies this as being a reflection, which is going to be the line of symmetry. And we have to identify our pre-image, so where we started, and then we have to identify our image, where we're going to end up. Okay, and so just like with translations, there's going to be like coordinating information here, and so the algebraic rule signals some kind of sign change. That's because we're flipping over a line of symmetry that has to track distances, and then the formal rule ties all those pieces together. Reflection over the line of symmetry that takes our previous image and takes it to a new one. Okay. So the last one was rotations. Now rotations are going to be kind of the weird one, and so I want to start with rotations, kind of roughing out a picture, but I'll try to bring you a better picture here in just a moment. So here's the deal with rotations. Again, as you found in your investigation. So the first thing you have to identify is a center of rotation, somewhere where which this thing is going to be spinning in a circular motion. And the default, and this is something we should really note here, the default direction is counterclockwise. Okay, so we always assume a rotation's happening kind of counterclockwise first, and again, a rotation is nothing more than just a spin. Okay, so let's start again. I'll start with the structure. So here's kind of the deal. You need a center of rotation. So that's what that thing is, a center of rotation, and then you need some circles upon which to travel. And the circles should use that center as part of the circle, and should use this point as part of its circumference. And so C is going to travel kind of along this line. We can switch it up, we can switch colors. And so A is going to travel again in a circle, but it's going to travel in a circle around the center of rotation. That's a terrible circle, but this is just rough. And then the third one is going to be for B, again using the center of rotation as the center of the circle. We're going to move around the whole entire thing. And so that's what it means to be a rotation. It's going to be A, B, and C traveling along these circles. These circles are terrible. I actually have a pre-prepared one, a picture, so it's going to be a little better for you. So let me just bring this up here and kind of overlay my picture. Give you maybe a better sense of what's going on. Let's actually delete this. Okay. So here in this picture, we actually took a computer tool to make my circles a whole lot more clear. We still have a center of rotation right here. Okay, that's still the center. Okay, and then we have the circles that use that center moving around. And again, please note that all the vertices appear on a different circle. So the last thing we need is just a angle of rotation. And so the angle that we're talking about, and I'm going to try to zoom as close as I can, has to be formed between the previous point at which you were moving the pre-image, the center of rotation, and then the circle again itself. And so to get into a fine point here, okay, this guy right here, that's my angle of rotation. As you can see, I just took C. Using this angle of rotation with the center, I now have a location for C prime. And I can repeat that for the other ones as well. Again, allow me to demonstrate. So if I take this point A and I bring it back to the center of rotation, okay, the angle of rotation has to be the same as the previous one, so this is going to be 90 degrees. And so I now have to rotate this 90 degrees until it hits my circle. And it's going to be a little off screen here, so let me bring that back. So I'll take this point and I'll rotate it 90 degrees along the circle itself, okay, until it gets about right there. And so that's going to be my A prime. And again, we can see the angle of rotation right there. That's going to be my angle of rotation as well. Okay. For this third point, which is going to be the pink one, we'll do the same thing. So we'll take this and we'll bring it to our center. Okay, so okay, and so we were going to rotate this 90 degrees. Okay, that's a little too far. Should go right there. Okay, and so again, we'll see that we have a 90-degree angle formed between the center of rotation and my two pink lines, and that's going to be my location for B prime. Okay? And so if we connect all three of these points, we'll have our new triangle, our image triangle. Okay? And so this would be B prime A, C prime. It's a little bit hard to see, so allow me to kind of fill in the triangle. Okay? And so we rotated from the orange triangle to the yellow one. So the structures we're talking about, the important pieces, seem to be two things. One, we have to have a center of rotation, which track which serves as the center of a bunch of circles that include the vertices. And then we need angle rotation as well. And so let's record that information here. Excuse me here. So the structural rule, the things we actually need are a center of rotation. And so these are the centers of the circles. And the second thing you need is an angle of rotation. Okay? So what you need is a center for all the circles upon which you're traveling these points, and you need like an angle so you know how far to actually make them travel. The algebraic rule, just like the reflection algebraic rule, there is one, but again, it's going to be different for every single rotation you do. And so it's not useful to maybe name it by name, but it might be useful to point out that two things are going to happen. One, you're looking for signs to change, and two, the other thing you're looking for is a flipping of the points. Okay? Because there's so many variations of an algebraic rule, just like with reflections, it turns out not to be really, really important. But it is really important uh, to know the formal rule. So the formal rule for rotations, we're going to start with a big R. This one right here actually had two different things that were important. One, we had 0, 0, because that was our center of rotation, and we had an angle of rotation of 90 degrees, and that took the previous triangle ABC to our new triangle A prime, B prime, C prime. Again, to label that kind of identify what's going on, the big R stands for rotation. These two pieces are the important information. That's going to be the center of rotation. Okay, and then the angle of rotation. And those should be, of course, the same. Okay, and that takes the pre-image and takes it to the image, which is just like the copy. Okay, so kind of just some really quick review. When we talk about the translation, we're talking about a slide. To know that it actually has been slid, we have to use congruent parallel vectors. Those are the brown things in this picture. We're using vectors because they go the same distance in the same direction. And so if you move all the vertices the same way, along all the same vertices or congruent parallel vectors, then you have a translation for sure. The algebraic rule for this one is actually kind of important because it kind of reveals for you what the vector is. And so the algebraic rule says go down to over 5.5. That's what the vector will be as well. And so if we write a formal rule, we have to use the vector because that's the most important thing. And so what's important to all rules is that you absolutely must, uh, identify and use the vector. Okay. For reflections, just a quick review, this is going to be a flip. And so if we're going to do a flip structurally, we need something to flip over. That's going to be your line of reflection, which you can identify by an equation or probably by a name. If you're going to be flipping over this line of reflection, that means you got to move directly to the line and directly away from the line using the same distances. Directly to the line means that you have to have the same. It means that the line of reflection has to be a perpendicular bisector to those connection lines. So if I connect B and B prime, C and C prime, A and A prime, the line of reflection cuts it right down the middle. Um, the algebraic rule for this one isn't honestly that important because there's so many different variations. But the structural rule, you must show the line of symmetry and it must bisect those pre-image image lines. So the formal rule reflects the important part, which is the line of reflection. And so important to all the rules for this is that you must identify and use a line of reflection, or line of symmetry, Okay, you must. Finally, rotations, which I know is probably the most complicated of the three. You're spinning in a circular motion, clockwise. I'm sorry, in this case, counterclockwise, in a big circle using an angle of rotation with the center of rotation. And so the important thing to this one, because again, the algebraic rule isn't really all that important. The important all rules that you must identify a center of rotation and an angle of rotation. Okay? Which, if you look, that's why the rule reflects those two things. Okay? So like now we have our last question. How can you tell if a shape has been translated, reflected, or rotated? And so the big takeaway here is that you must be able to show the structure. Whatever that structure may be, and you must be able to write a rule. Okay, and because the algebraic rules are really not that useful all the time, this is going to be the formal rule. Okay. Guys, I know that video was really long, but there's lots to consolidate and cover, so thank you for being persistent and sticking with it. So now once you kind of finish your notes, and you finish your notes by writing a conclusion, of course, come get me, and I'll start you on a little bit of practice before you take your quiz. All right, again, sorry about the length of the video, but that's sometimes how it has to be. Thank you very much.